Welcome to another video. If the lighting on this video is not as good as the other videos are, forgive me, I'm still working on the setup. As you can see, I am teaching linear transformation. I am not going to be solving any problems because I think I'm beginning to drift completely away from the original goal, which was to explain concepts to many people. So I'm doing linear transformations in linear algebra. I'm making this video because I believe that if not today, tomorrow, or in a year's time, it's going to save someone's grades and understanding also. And it's also a good review for those of you who did linear algebra, whether basic linear algebra or advanced linear algebra. We're going to cover most of the concepts on linear transformations. Let's get into the video. For full disclosure, if this video looks too basic for you, maybe you want to come back another day, because this one is for those who are struggling with linear transformation or who don't even know what it's all about or who just want me to break it down. So this is for the babies. Okay, I'm going to start from the most basic thing that you know, a function. You see, for a function, what a function does is it takes from somewhere, it does something to the input. So it takes an input, it does something with it, and it gives you an output. Where you take the input from is what you call the domain. What you get is in the codomain. Okay? So these two words will be represented by V and W. So remember that. When you see me write V, I'm talking about the set of all the inputs. Okay? When you see me write W, I'm talking about the set of all the outputs. So if I take a number and I find the square root of it, like the square root of 4, and I get 2. 4 came from the domain, from V, and 2 is going to be in the codomain, the output. I'm taking square roots now. Okay. Let T be a function. Then T takes from V and puts it in W, where V is what we call the domain and W is the codomain. That is super basic. You see, these two guys will cause us a lot of trouble, the domain and the codomain in the future. Okay, but for now, let's just understand them. Now, what is inside V? It could be a number. It could be a set of numbers. It could be a matrix. It could be a function. It could be anything. As long as we can do something to what is in V, and it only produces one unique output in W, then we say T is a function. That is the definition of function you learned in Algebra 1. Okay, but we don't want to use the word function because you see, function will have to take an input, do something to it, and then we start graphing it. Some of these things cannot be easily graphed. So we don't use the word function here. We say it is a transformation. Okay? Now remember, you also learned there are different types of functions. You got linear functions, you got quadratic functions, you got cubic functions, you got logarithmic functions, exponential functions. Yeah, but here, now, we're not going to be using the word function. We're just going to say it is a transformation. That's why we chose the symbol T. So, when is it linear? We're going to talk about that. So remember, what you have in V, the domain, could be a number, a set of numbers, could be a vector, could be a set of... It doesn't matter. The most important thing is everything can be represented as a vector. Once numbers are involved, you can write as a vector. So that's the perfect reason why we chose giant V as the domain because everything we're dealing with is going to be a vector. Okay, now, and this is where we're going, okay? This is the world. You're going into the world. I don't know why they chose W, but after V, TU, V, W. Oh, it's W to the right of V. That's the reason. I was wondering. I just realized that. I didn't. Okay, so V goes to W. Now, just as we had linear functions in algebra, a transformation can be linear. How can you say it is linear? If you take anything from V, or any two things from V, okay, and you try to transform them together. Let's say this guy is made up of just quadratics. Okay, let's just say this is the home of quadratics. So you got two quadratics and you want to differentiate the two quadratics. Okay, let me just do something here. So let's say what t does to quadratics, let me write x squared minus 1. What t does, the function of t is to differentiate the quadratic, okay? So it's a differentiation transformation. Remember, this is going to be 2x. Notice what has happened, that this quadratic has become a linear function. Let's say there is another quadratic, t of negative x squared plus 2x minus 1. Okay? What will this be? If you take the derivative of this, you're going to get negative 2x plus 2. The first condition for t to be a linear transformation is that t is linear if the t of any two functions, x plus y, ignore what I'm using there, okay, equals t of x plus t of y for all x and y taken from the domain. So if you take any element, so now we're saying, ignore what I just wrote here, I'm just looking at this now. Let's say x and y came from inside V, and you transform the two of them together by addition, then you can get the same result as if you individually transform them. That is one characteristic of linear transformations. Okay? So, which is what I'm about to show here as a good example. So let's say this is a quadratic that represents maybe our x, a vector, and this is another vector coming from here. They took the two of them. You can transform them separately, but you can still transform them together. Watch this. You notice that if I add them together first, let's say I add x squared minus 1 to negative x squared plus 2x minus 1. Well, notice that what I'll be doing is I'll be transforming, let's clean this up. Oh, this is gone. There's no more x squared. Now I have minus 1. I have only 2x. I have minus 1, minus 2. I have just 2x minus 2. So after simplifying, this is what I need to differentiate. Now if I differentiate 2x minus 2, what do I get? My answer is just 2. So when I first add them together, before transforming them, I get 2. Will I get the same answer if I transform them individually and then add the two of them together? If I add this to this, what would I get? Boy, I'm going to get 2 because this minus this is 0, and then I have just 2 as my result, which is the same answer that I'm getting here. Do you see that? That is beautiful. That is the whole concept of linear transformation as far as addition is concerned. There is a second condition that you need to know. What's the condition? That this is condition 1. The second one is that t of a scalar multiple of any vector, any input vector from V, let's say c times x, is equal to c times the transformation of x. You can also still use differentiation. In fact, for your own safety, it is better if you just assume that a linear transformation is I'm taking derivatives. Whatever you can do with derivatives, it's going to happen for whatever type of transformation you're dealing with. Okay, it will save you. At least it will help you understand if it's a linear transformation or not. Maybe not the best example, but this is easy to understand. So suppose, now what is C? C is a scalar quantity where C is from some field, okay? Some field of numbers. Remember, a field must have all the things inside a field must be able to add and stay in the field or multiply. So this is why it's easy. So this number could be a complex number, or it could just be or a real number. Okay, but for the sake of this example, I'm just going to stick to real numbers for now. So this is the second property. You notice that if I say you should differentiate d dx of x squared, and I multiply it by 3, this is the same thing as 3 times the derivative of x squared. So you get the same answer. What's the answer here? It's 6x. What's the same answer? Is 3 times 2x, which is still the same thing as 6x. These are the two properties of all linear transformations. Now, there are some results that come from this. One of the most obvious one is that if we change the sign to a minus, it's more like you're dealing with a negative vector in here to be y. It's t of x plus, because it's now going to be minus 1 times y. Okay, now because of these two happening, we can combine these two together and say, you know, instead of writing x here, what if I just put c of x here? Okay, so generally, we can show, come on, here's show. We can show that t is linear by saying t of c of x plus y, the transformation of c of x plus y is equal to t, watch this, t of c of x plus t of y. But we know from this second condition that t of c of x can be written as, let's write it here, c times t of x plus t of y. This is the one stone that kills two birds. If you can do this, then you don't have to do these two together. Now, sometimes it's not easy to do this, but if you can see this coming, hey, if you can see this coming, then you don't have to do these two separate checks to know if it's a linear transformation or not. I'm going to take one example, and in the next video, I'm going to go into other things. Okay, it's going to get gradually more complicated. This is just for you understanding the concept, and differentiation is your best friend in this case. Let's take one example. So I'm using the first example in the book, and when I first took linear algebra, I did not understand any of the things that are on the board because I was not exposed to it. I was just quick to do calculus. I was quick to do all the algebra. But when I first heard of linear algebra, I thought basically I would be doing a lot of algebra of linear functions. But when this came up, it was just strange. Now, so we have a function that takes points. You see this thing called R2? It is that thing you graph on. You see this thing, the Euclidean plane? This is R2. So here, this is the real number line. So all real lines are on the number line. Now we now find another number line and we switch it to point up. We call it the y-axis, but that is another R. So when you pick a point here, this point is defined by two R's. This is R2. So if you pick this point, let's say this point is 1, this point is 3. You call this point the point 3, 1, right? Those 2 points are in R2. And that's how you write them, A1 and A2. We could have said X1, X2, But so we are transforming a point. We're going to move this point. It's either we move this point away or we bring it down here. The way we move this point around on the plane is what t is doing. Where will the point end up? Will it end up on a straight line, on the number line, on the x-axis, the y-axis, or will it still stay on the graph away from the line? Well, look at it. It takes a point from R2 to R2. So which means that you're taking this point and you're going to move it somewhere else. Using this rule, how do you know where it's going to go? Well, this is what you got to do. We just want to know if this is a linear transformation or it's not. Can you do it to 2 points at the same time? Well, we have to look at those conditions that we said t must satisfy. So understanding this helps you do the work. This point is going to move. Oh, the first, we don't even know the point, okay? We're just going to call it A1, A2. So what are we supposed to look for? Remember, to show that t is linear, we could do the first one. We could do t of x plus y equals t of x plus t of y. Then we go back and say t of cx must be equal to c times t of x. We could do this. But remember what I told you, as long as you can see the future, you can tell, hey, why don't I just, instead of writing x here, I can write cx here and see how this goes. So that's what we're going to try to do in this exercise. What we want to show that t of c times, okay, let's just write it. T of c times, this is what is being transformed. But you see, you have A1, A2. We need another one because we need two of them. Here we have just 1 point. We'll need to get another point. We manufacture the point, so we can just call it, instead of using A, we might just look for other letters to use. We can just say, oh, we could use X and Y. We don't care, right? Okay, so let's define 2 other points. 1 point is going to be, you know what, let's not use X and Y. Let's use B and D because we're going to use C and we already have A. So the book actually uses B and D. So let's pick 2 points. Let's pick a point B1, comma B2. And let's pick another point D1, comma D2. Okay, so we're going to transform these 2 points together and see if it's going to obey the rule that we wrote here. Remember, if we put these 2 together, we're going to get t of cx plus y equals c times t of x plus t of y. This is what we want to accomplish. 1 bird, 1 stone to kill 2 birds. So we say let b1 comma b2 d1 comma d2 be elements in R2. Okay, so let them be here. Now we want to do the transformation. We want to show that the linear transformation of, we're going to multiply this by c, the first one. This is our x in this picture now. Okay, where is it? This is our x. Our x is this point. So this is more like your x and this is more like your y. So it's going to be c times this 2. This is b1, comma b2 plus, this is your y, d1, comma d2 will be equal to c, I may have to extend it, it will be equal to c times the linear transformation of b1, comma b2 plus the transformation of d1, comma d2. Yes. Okay, we just want to be able to show this. Okay? And if you can show this, you are perfectly fine. This c is multiplying the transformation. So let's begin the algebra. because this is where we start. What is the rule we must follow? The rule has been given. To transform a point, you double the first input, the domain, double the domain, add the codomain. Okay? See the point? 3, 1. You double 3, you add 1. Double this, add this. Then put the 3 in place of this to create the new point. So the transformation of this, based on this rule, would have been, we're going to double the 3 and add 1. So we're going to get 7. And on the right-hand side, it's going to be what used to be the domain, which is 3. So this is the point. So the transformation of 3, 1 would have been 7, 3. Okay? Which has got to be somewhere here. So it's more like you're stretching it and then you're angling it. I don't know if it's the same thing. Do you see that? So what do we do here? Let's begin with this process. This is the same thing as the transformation of this distributes into this. It's going to be CB1, comma CB2 plus D1, comma D2. Okay. So this is the transformation that we have. All I did here is I just distributed this. So you know, because these two are vectors from, remember they're vectors because you got this, you got this, you got this. You could have written them as just vertical strips. You can add the corresponding parts together. So this gives you T of, well, this is going to be CB1 plus D1, CB1 plus D1 plus, comma rather, CB1 plus D1, comma, because now we have the two of them together. It's going to be CB2 plus D2. So here, we now have something to transform. We can now apply the rule that we have, because this A1 is all of this, and this A2 is all of this. You see it? So we can go on and say, what is the rule? The rule is to double this and add this. So this is going to be equal to, so this is equal to, we're going to double this and add this. So it's going to be 2 times CB1 plus D1. Okay, we're multiplying this. Then we're adding. What are we adding? We're adding CB2 plus D2. CB2 plus D2. Okay, so if we add this to that, that's one part of our giant term, and then this one is not term, a giant point vector. So, and then the next one will be, this replaces the right hand side. So it's going to be CB1 plus D1. CB1 plus D1. There you go. So here, this completes the transformation. All we have to do is simplify what we have here. You see, linear algebra has gone, it's algebra, but you have to be careful what you write. Do you get the transformation? Give me a thumbs up if you get it. If you don't get it, just go back and follow the steps again using this rule. The rule is you double this one. And remember, this one is all of this. How did we get all of this? We just simply added these two together because they are vectors. And remember, in a vector space, you must be able to add vectors together. And these are like matrices. Okay? It's like you're writing CB1, CB2. Okay? A matrix. And you are adding it to this one, D1, and then you have D2. By the way, after a while, this is what we'll be doing. We will not be doing these horizontal presentation. It becomes vertical because with this, it's easy for you to see that we're adding these two together. That's how we got this. We have to multiply by 2 first. This one by 2, then you add, okay, 2CB1 plus 2D1 plus CB2 plus D2. Okay, we have a comma, and then we have CB1 plus D1. Okay, so at this point, I know how this looks, okay, because I know the 2's, because of this definition, all the 2's need to be on the left. So what I'm going to do is take everything that has a 2 to stay on this side, okay, and the C's will have to be on this side too. So I might as well say, this is 2CB1. Do I see another 2C anywhere? Oh, I got 2D. But I got a CB2 here, and I got a CB1 here. Okay, I can't have the two CB1s here. So this is separate. So what do I do here? I do 2CB1 plus CB2 plus 2D1 plus D2, comma, CB1 plus D1. Okay, it's going to look really clean now, because what I have here is I can actually separate this. So if I take this 2CB1 plus CB2, and then I take this CB1 and I bring it here in a comma, I can separate these two so that I have 2CB1 plus CB2, comma, CB1. Ooh. So I have this here, and I can add it to whatever I left out. 2D1 plus D2, comma, D1. Ooh, do you see what's going on? So I have two different parts here. Can I narrow this down? This is the same thing as what can come out? C. This is C times, this is going to be 2B1 plus B2, comma, B1. I've taken out the C's. Everybody has a C, right? And here, plus, what can come out? Nothing comes out. It just stays that way. 2D1 plus D2, comma, D1. Notice that what I have here is basically C times the transformation of B1, comma, B2, according to this definition. I just C times this transformation, because this transformation is going to give you this according to this definition. And this is plus. What is this? This is just the transformation of D1, D2. I chose to take this challenging one, okay? Again, you don't have to do it the way I did it. Some people will take this, simplify it, and stop at this point, and then start from here, work through it. If you work this backwards, you're going to get to this point also. That might be a less stressful way, but this is a nicer way, because I've been able to show that this is equal to this, which was what I was targeting from the beginning, using the definition by combining the first condition with the second condition. I think this is a good place to stop. Let me give you a T to test if it's linear or not. In fact, it's going to be linear. You just want to make sure that you do the work right. Remember, write what you need to get and then show that this side equals this side, or you can go from one side to the other like I did here. This might be a little bit more technical, but just do it. When you get to a convenient place, you stop, and then you start from the other side, from this other side, and you get your answer. Let me give you something easy. Okay, in case you want to just practice, you might just work with this one. So this is a transformation. We don't know if it's linear, from R3 to R2. So you're going to have 3 entries, okay? So say X, Y, Z will be the axes that are involved in this, or the dimensions, okay? And then what happens is it compresses into, or it shrinks into 2 dimensions, because one of them vanishes. What you have is going to be a 2D, where how you form the input, in this case here in R2, is you subtract this from this. And then if you want to form the output, in this case, it's going to be just 2 times the Z component here. So we want to see if that's a linear transformation or not. It is important to practice this, because when we start getting to null spaces and range and image and the kernel of anything, any transformation, then we have to be able to do this comfortably. Okay, I'll handwrite what I think is the easiest way to do this, and then you can leave a comment in the comment section. I'll post it either in the community or attach it as a file somewhere. Never stop learning. Those who stop learning, stop living. Bye-bye.